If I want those videos online, I have to record them sometime. So here we go. As I mentioned, today's lesson, the notes that you received, they look really, really jam-packed. And yes, they are. But a lot of what they're jam-packed with is vocabulary that you've seen before and a little bit of new vocabulary, which is pretty intuitive. All right, so we know what a circle is. We know that it is a set of points in a plane, and all of those points on the circle are equally distant from a given point, and we call that given point the center. We know that the distance from the center to any of the points on the circle is called the radius. It's vocabulary we already know. We already know that a diameter goes from one side of the circle to the opposite side, cutting through and passing through the center. We also know the relationship between the radius and the diameter. What is the relationship between the radius and the diameter? One person, please. What is the relationship between the radius and the diameter? Radius is half the diameter. Okay, and it should make sense that in order for two circles to be congruent, they would have the same radius. Gentlemen, are we up here? We focused on something that doesn't have to do with what we're trying to do here. Thank you. All right, so now let's talk about new vocabulary. In order to expose you to this vocabulary, I'm using problem 1 as kind of a visual example. So notice in problem 1, I have angle BCA, and I'm telling you that it's a central angle. So how might you define a central angle? How might you define a central angle? What makes it a central angle? What's at the center, Jesse? Whatever that dot's called. What do we call that point? The vertex, yes. Okay, so I apologize. The line that I'm giving you for this isn't long enough, but the central angle is an angle having the vertex at the center. You probably already know what a semicircle is. Half circle. What is the measure of a semicircle? Well, if the measure around a circle is how many degrees? 360. Then it should make sense that a semicircle is 180 degrees. Such as, for example, arc BED is a semicircle. So a minor arc, like arc AB, is what? If I compare it to a semicircle, is it less than a semicircle or greater than a semicircle? It's less than. Whereas a major arc, and apparently I did something goofy in my notes, it says BDE instead of BDA. Is that correct? Okay, that is correct, actually. BDE is also a major arc. I don't know why it's different here than it is there. And it's greater than a semicircle. So the big important thing that you need to be aware of as far as finding the measure of an arc is that it's basically, especially if I'm looking at a minor arc, the measure of a minor arc is the same as the measure of its central angle. So, for example, again, just as an example, if I told you that the measure of arc BCA was 60 degrees, you would be able to tell me that the measure of arc AB is also 60 degrees. Now, you notice in your notes it says that a major arc is 360 minus its central angle. This is what I mean by that. If I was asking you for the measure of arc BEA, does that visually make sense to you that it's 360 minus that little chunk that isn't included, the 60? Does that make sense? Okay. And then finally, we've dealt with part plus part equals whole before. We've dealt with taking two angles that are parts of a larger angle and adding them together to find a larger angle. We've taken two segments and added them together to get a larger segment. And same property applies here. Part plus part equals whole also works when we're talking about arcs. So in problem 1, yes ma'am. A major arc is more than 180 degrees, whereas a semicircle is exactly 180 degrees. As far as the difference between how we name them, you may have noticed a major arc is named with 3 letters. A semicircle is also named with 3 letters. Thank you for kind of bringing it to my attention. You might want to jot down somewhere in your notes that a major arc must be named with 3 letters. Semicircle can go both ways. 2 letters or 3 letters is acceptable. Minor arc, I don't know why sometimes the book uses 3 letters. It makes no sense to me. It's considered proper to only have 2 letters for a minor arc. But definitely must have 3 letters for a major arc. So in problem 1, we're just making sure that we're speaking the same language and able to identify minor arcs, major arcs, and semicircles. So in problem 1, part A, what are the minor arcs of circle C? Arc AB is one of them. Give me another one, Jesse. DE. Okay, I'm sorry, I heard something. BE is also a minor arc. And that was almost spoken hesitantly, like, I don't know, maybe it's a minor arc. And that brings to mind something that I want to point out to you, ladies and gentlemen. Just because that arc BE is formed by an obtuse angle, doesn't matter. It's still a minor arc because it's less than 180. Okay, so yes, AD will also be a minor arc. Semicircles, I named one up here, arc BED is a semicircle. There's a few more, Zoe. Arc BAD is also a semicircle. Michael. Arc AED, I'm sorry, ADE. And one more. ABE. And then finally, major arcs that contain point B. Containing point B is not necessarily, or is not the same as having B as an endpoint. Okay, it doesn't have to have B as an endpoint to say that it contains the point B. Helena. Arc, say it again. Arc EAD is a major arc containing the point B. Give me more. Okay. So, fantastic question. Realize when you're looking at these major arcs, it's sometimes helpful to trace it and realize what you're tracing. You're starting at point E, passing through point A. You see how I passed through point B while I was at it? And ending at point D. That arc does contain point B. There's more. Need more. Grace. Say that again, please. Arc BAE, yes. I think there's 2 more. DA, what'd you say? Be careful. DAB, notice, is a semicircle. Oh. Michael? Arc EBD, be careful, do you see, is actually the same as arc EAD. You're just naming it a different way. Okay, so there's no reason to name it again. We've already mentioned that arc. How about arc DEA? I'm sorry, say that again? Fantastic question. Let me show you DEA in blue and DAE in black. That one starts at E, passes through A, and ends at D. Whereas DEA, starts at D, passes through A, you see the difference? Or E, passes through E and ends at A. It's a different arc. And here's a big tell, Michael, on how it's a different arc. Look at the endpoints of the arc. Notice that they're different. So they are definitely two different arcs. I think there was one more. E, say that again, I'm sorry? B, D, A. Yep, that's the last one. Thank you. Got from this screen what we need? Okay. Let's take a look at identifying the measures of arcs. So a couple of typos I need to fix on this screen. This should just be arc TU. This should just be arc RU. So in problem 2, let's find the measure of arc TU. It's right there, staring at you. It's 60. How about arc TUR? That one's 180. Good. Arc STU. That one's 80. And then finally, the measure of arc RU is 120. Looking good so far? Okay, so once again, yes, these notes are jam-packed with stuff, but a lot of it is very intuitive. A lot of it is refreshing our memory. So there's a your turn for these two problems. Please work through those within your group. Okay, please finish checking your answers for the your turn 1 and your turn 2. Make that a little bigger for you. And if you have any discrepancies, any confusions, any, uh-oh, I didn't get that, Alina, of part number 2? Yeah. All right, so in part B here, you're asked for the measure of arc RS. Does it visually make sense that arc PS is a semicircle? Yeah. Okay. All right. And then, do I still need to talk about part D? Yeah. Okay. Part C. Arc PRQ. Do you see arc PRS? Remember, we just finished talking about it, is a semicircle, 180 degrees. PRQ is that semicircle plus this little 28 degrees. So 180 plus 28. Yes? Part D, arc PQR is what I'm asked for. So if I were to trace it, do you see that it starts at P, goes through Q, and ends at R? So it's pretty much the whole circle, the 360, without the 77 degrees. Yes, ma'am? Part C on number 1, major arcs are, what did you get? Or what did you miss? Or did you name something twice? SRQ. Because silly Mrs. Clouse didn't write it down. Thank you. SR.
And then I got PRQ.
Q.
Okay, that was
PRQ is here.
Okay.
QSR
Yeah, I got QRF.
would be the same as QPR.
What about S?
S
Oh, just kidding. Wireless is the same.
QP would be the same as SRP.
Then I got QRF.
Say that again?
QRF.
QRS I have right here. You just gave it to me as SRQ. You named it twice, it sounds like. Right, remember, just like way back in chapter 1, when I told you that segment AD was the same as segment BA. Same idea here. Yes, okay.
What about
SPR is the same as SQR, which I have as RQS. Yes, ma'am. SQ is a minor arc because it is less than 180. Don't confuse acute and obtuse with major and minor. Yes. And that's where that third letter always comes in. If it's just 2 letters, you're going the shortest distance between those 2 points. If you're trying to go the longer distance, that's why you need that extra point in there. Okay? Any other questions up here? All right. So on to talking about circumference, which we've seen before. Remember, on the reference sheet, you have 2 formulas for circumference. They are 2 pi r or pi times diameter. Pi r squared, be careful, is the formula for area, which has to do with tomorrow's lesson. Hold that thought. Okay, these are the formulas for circumference. Remember what circumference is. Circumference is the length around the circle. That significance of my sounding silly will come into play later. All right, so in problem 3, I have a merry-go-round with some of the seats being 7 feet from the center and some of the seats being 10 feet from the center. So what we have here, notice, is concentric circles, and you have the definition right there in your notes. Concentric circles are just circles having the same center, but not the same radius. So on this merry-go-round, I have concentric circles, where this radius is 7, and this radius is 10. And if I had one of my children on one of the seats and another child on the different seat, I bet you they would argue that one of them got to go longer, because that's the case. This guy sitting in the middle isn't merry-go-rounding for as far a distance as this guy on the outside. So that's what this problem is asking us. How much further is the child sitting on the outside actually traveling? So does it make sense that I need to find the circumferences of my 2 circles? Okay, so let's find the circumference of the large circle. That's 2 times pi times 10, giving me 20 pi, and I'm not going to evaluate the pi yet, just because it'll facilitate my calculations later. And then I'm going to find the circumference of the small circle. Well, that's 2 times pi times 7, giving me 14 pi. Do you see what I mean about making the calculations easier? How much bigger or how much further? 6 pi. And now, let's evaluate that pi. So the difference is 6 pi, which is approximately 18.8 feet. The instructions didn't specify, and since this is a real-world situation, I would expect you to round. To the nearest tenth is usually a good rule of thumb. But here, okay, you have a problem very much like it in the your turn. Please take a moment to work through that. The outer tire will travel approximately 29.5 feet further. Okay, the circumference of the large circle is 32.2 pi. Say that again? Okay. And then the circumference of the smaller circle would be 9, no, I'm sorry. The difference between them is 11.4, so 22.8 pi. Where am I getting the 11.4? Notice this time they didn't give you the smaller radius. They gave you the distance between the two circles. So you'd subtract the 16.1 minus the 4.7 to find this smaller radius as 11.4. Okay? For the second problem, what I quickly want to show you is if they're talking about the radius of circle A, being equal to the diameter of circle B, does it visually make sense that circle A is twice as big as circle B? Hence that 2-to-1 ratio. Yes, ma'am? If you added okay. If you added it, you'd be finding a circle that's bigger. So you'd be answering a completely different question. Yes, you would end up with the same answer because what ends up happening is that the pi kind of factors itself out, and it's just, well, not so. It's basically as if you're finding the circumference of a circle having this distance as your radius. Okay. You were with me here and here? Okay, if I subtract these, I've got 9.4 pi. And if I do 9.4 in my calculator times 3.14, that's approximately 29.5. All right, so on to finding the length of an arc. Remember I told you earlier that circumference is the length all the way around the circle. So does it make sense that the length of an arc would just be a fraction of that circumference? Two different ways that you can think about this, okay? You can think about this as this is a fraction of the circumference. So you find the circumference and then take a fraction of it, and that fraction would be what part of the circle your arc is over the whole 360. So it would be arc measure you would take arc measure over 360 and multiply that by the circumference. You could think of it that way, that arc length is just a fraction of the circumference. Or you could think of it along the lines of a proportion, where the arc measure is part of the whole 360, and the arc length is part of the whole circumference. So that proportion would look like this. Arc measure over 360 equal to arc length over circumference. You know how your brain works best. I'll do one way and the other a different way. Okay, so problem 4, part A, I'll do the red way. So I'm trying to find arc CD. What is the measure of arc CD? 90. And what fraction is that 90 of the 360? 1/4. Okay, so let's make sure that I'm showing all of my steps. I'm taking 90 over 360 and reducing that and getting 1/4. And then I take that 1/4 times the circumference. Well, this time they've given me the diameter, so finding the circumference is easiest by doing pi times diameter. So my arc length is just 9 pi over 4. And let's leave our answers in terms of pi. Be ready, however, for your notes to ask it of you either way.
How did you get the 9 times 4?
Okay. Were you with me here? Were you with me in finding the circumference? Okay? Remember, you're just taking that fraction and multiplying it by the circumference. Remember how you multiply fractions: straight across the top, straight across the bottom. 1 times 9 pi, 9 pi. 4 times 1/4. That's it. Okay, as I said, let's do part B the other way so that you can judge for yourself which method makes the most sense to you, which method are you more likely to keep in your brain because it's not on the reference sheet. And I can almost guarantee you'll have either an arc length problem on the EOC or you'll have a sector area problem. We'll talk about that tomorrow, but it's the same principle. Okay? So you have to make some sense of it and be able to translate it for that EOC, because I can almost guarantee you'll see something like it there. All right? So, arc STR. What is the measure of arc STR? Look at it. What's the measure of arc STR? It's 260. Good, good. So 260 over 360 equals the arc length that I'm trying to find, which is x, over my circumference, which is 8 pi. Before I go any further, if I've lost you somewhere, you don't know why I put something where I put it, yes ma'am. Notice what arc, I made this mistake yesterday. Notice what arc they're talking about. They're talking about this arc. You would do 360 minus the 100 they gave you. Excellent question. When you're doing your cross-multiplying calculations, I would say leave the pi out and then just tack it on at the end. Yes, sir? Formula for circumference is 2 pi r. Okay? So before you cross-multiply, however, look at these numbers. These are big, and they're reduced. So if you can reduce a fraction, you probably want to, just to make your life a little bit easier. So in my scientific calculator, I enter that 260 over 360 as a fraction, and my calculator reduces it for me. It's 13 over 18 equal to x over 8 pi. And that's just a little bit nicer to look at in my cross-multiplying. Say that again? Now we cross-multiply, yeah. So we have 18x equal to 13 times 8, which is 104 pi. And eyes up, please, because some of you are still not quite familiar with how to do this in your calculator. What's the next step in my equation solving here? Divide both sides by 18. But if you take that 104 and divide it by 18, is it nice and pretty? I don't think so. All right, so instead of taking in your calculator and dividing 104 by 18, in your scientific calculator that you should have by now, take that 104 over 18. Type it in as a fraction. Okay, and your calculator spits back a mixed fraction. You don't want a mixed fraction, you want an improper fraction. Your calculator will do that for you as well. You go shift button, second button, whatever the button is that brings up your second functions, and then your fraction button, and it gives us a nice, pretty 52 pi over 9. In your calculator, type in 104 over 18. Type it in as a fraction. And hit equals. Your fraction button is A with a B over C. It's probably in the upper middle. It gave you a mixed fraction, right? Oh, you have the exact same calculator I do. Okay, your shift button is all the way up here. Hit that, and then the fraction button again. It should give you 52. No, we don't have time. And then tack on top.
So I think you don't mind. I was like,
Okay, in your calculator, there's two separate fractions. So you do 1/4 over 18. And it gives you this. Okay? And then you hit this button, change it. Oh, wait. Hold on. Yeah. 1/4 over 18. I'm pretty sure I'm not going to see it. Right. Realize that it's a gridded response question. They have a range of answers that they'll accept. It's a multiple choice question, which is pretty Oh, there we go. Auto simplify. Bye-bye. 1/4 over 18. And then second fraction. No, thanks. Second fraction. 52 over 9. Hello, hello. Remember, put your technology away. Please grab one of my technology. Oh, darn, I've been recording this whole time.
I had no idea how to do the whole process.
Oh, yeah. That has to do with today's lesson.